Hello guys, Kamiti here. This is Kamiti Structural Engineering e-learning platform, and today we are going to analyze a flame whereby we are going to plot its bending moment diagram. And last time we said that a flame is a structure which is composed of vertical and horizontal members. The vertical members are known as columns. So we got a vertical member BD, so that is a column, and then we got member AB and BC, that is a beam, and the member AB is loaded with a point load at E of 10 kilonewtons, and the member BC is loaded with a uniformly distributed load of 2 kilonewtons per meter. Ladies and gentlemen, subscribe, hit the notification bell. Every time we record a video, you will be notified. Now, we are going to begin with the calculation of the fixed end moments. That is always the first step. So, step number 1, determine the fixed end moments. And in this case, we are going to begin with the span AB. So, fixed end moment for span AB, or in span AB. In span AB. Yep, the fixed end moment at A is an anti-clockwise moment, so it is going to be given by negative W AB squared divided by L squared, since the span is loaded with a point load, and that's the formula. So this is going to be equal to negative W 10 kilonewtons. So negative 10 multiplied by A, the distance from A to E, which is 2 meters, multiplied by B, the distance from E to B, which is 3. We got that squared, then we divide by the whole span, A to B, that is 5 meters, and we square it. So that is going to give us a fixed end moment at A of negative 7.2 kilonewtons meter. Then from there we go to the fixed end moment at B, which is going to be a clockwise moment. And for a clockwise moment, the moment is going to be positive, and it will be given by this formula, WA squared B, divide this by L squared. So remember always, when we are determining the fixed end moment at A, we are squaring B. When we are determining the fixed end moment at B, we are squaring A. Always get that difference. So that will be given by positive 10 multiplied by 2 squared multiplied by 3, divide this by 5 squared. And this is going to give us a fixed end moment at B of positive 4.8 kilonewtons meter. Then we go to the span BC. So in span BC, the fixed end moment at B, the span BC is loaded with a UDL of 2 kilonewtons per meter. Therefore, the fixed end moment at B is going to be an anti-clockwise moment, and it will be given by negative W L squared divided by 12. Negative because of anti-clockwise moment. So this is going to be negative 2 multiplied by the span B to C, 3 meters, so that is 3 squared, then we divide this by 12. And when we do so, we are going to get a fixed end moment at B of negative 1.5 kilonewtons meter. Then we go to fixed end moment at C. That is going to be a clockwise moment. For a clockwise moment, we are going to have positive WL squared, divide this by 12. This will be given by positive W, which is 2 kilonewtons per meter, times the span 3 squared, divide this by 12. and that's going to give us a fixed moment at C of positive 1.5 kilonewtons meter. Then we go to the span BD. So for span BD, in span B to D, the fixed end moment at B as well as at D are going to be 0 since the member BD is not loaded. Therefore, FB and FD are going to be 0. Then after determining the fixed end moments, the next step will be calculation of stiffness factors. So stiffness factors for members BA, BD and BC. So stiffness factors for members BA, then BC and BD. So we got that main joint. The main joint here is B. So we got the stiffness factor for member BA, member BC and member BD. So that's what we are going to determine. Now, starting with the stiffness factor for member BA, that is KBA, the stiffness factor will be given by 4EI divided by L. 4EI divided by L since the beam is fixed at A. This will give us 4E multiplied by I, which is 2I for member BA. So multiplied by 2I. Then we divide this by L, the span AB, which is 5 meters. And this is going to give us 8EI divided by 5. By that by 5. Then we go to stiffness factor for member BC. So for member BC, we are going to have 3EI divided by L. 3EI divided by L since the beam is simply supported at C. So simply supported 3EI over L. So this will be given by 3E. Moment of inertia for member BC is just I. Therefore 3EI divided by the span BC, which is 3 meters. And this is going to be EI, since 3 and 3 are going to cancel out. Very good. Then we go to the stiffness factor for member BD. So KBD, that will be given by 4EI divided by L. 4EI divided by L since the beam is fixed at D. So this is going to give us 4EI. I is just single divided by the span B to D, which is 3 meters. So that is going to be our stiffness factor for member BD. Now, after determining the stiffness factors, we are now going to determine the summation of stiffness factors. That is adding the 3 stiffness factors. So that is going to be KBA plus KBC plus KBD. And this is going to give us KBA 80I over 5. So we got the following summation of K. So summation of K will be given by 8EI divided by 5, that is KBA, plus KBC, that is EI, plus KBD, we got it up here, this is 4EI divided by 3. And then when we add the 3 stiffness factors, They are going to give us a total of 59 EI divided by 15. So that is the summation of stiffness factors. Then after calculating the stiffness factors, the next step, the third step, will be determination of distribution factors. So distribution factors for members BA, BC, as well as BD. So distribution factors for all those three members. Now, starting with the distribution factor for member BA, it will be given by stiffness factor for member BA. We divide by summation of stiffness factors, and this will be KBA, which is 8 EI divided by 5. Then we divide this by summation of K, which is 59 EI over 15. And when we do so, we are going to get a distribution factor for member BA, distribution factor of 0.407. So that is DFBA. Then you go to distribution factor for member BC. That will be given by stiffness factor for member BC, KBC, divided by the summation of stiffness factors. And this will be EI, which is KBC, divided by summation of stiffness factors, which is 59 EI divided by 15. And that is going to give us a distribution factor for member BC, distribution factor of 0.254. Finally, distribution factor for member BD. So for member BD, that is going to be stiffness factor for member BD divided by the summation of stiffness factors. This is going to be 4 EI divided by 3. Then we divide this by summation of stiffness factors, which is 59 EI over 15. And that is going to give us a distribution factor of 0.340. So we now have all the distribution factors that we need. So the next thing will be filling our distribution, or plotting our distribution table. We distribute till you get the final moments, which will help us to plot the bending moment. Done. Very good. Yep. So a lot we are going to have. So this is now how our distribution table is going to look like. I have just decided to complete it to save on time because it takes time to fill it. So I'll just explain what you are expected to do. Now we have the joints, and in this case on our beam we have 4 joints: joint A, B, C, as well as D. I have written them here: joint A, B, C, and joint D. On joint A, we got member AB, or span AB. I've written it there. On joint B, we have 3 members: member BA, member BD, and member BC. So we got member BA, BD, and BC. For joint C, we got member CB, which I've written there, CB. And for joint D, we have member DB, which is the last joint at that end. Then below the spans, we have the distribution factors. We had already calculated them. I load them up here. So the distribution factor for member BA is 0.407. That for member BD is 0.340, and For member BC, 0.254. Then below the distribution factors, it is followed by the fixed end moments, and we had already calculated all the fixed end moments. The fixed end moment at A, negative 7.20 kilonewtons meter. Fixed end moment at B for span AB, we got it as 4.80 kilonewtons meter. For span BC, we got fixed end moment at B, which is negative 1.5. So we got it here, negative 1.5. And for member, that is for the fixed end moments at C for members BC is positive 1.5. So positive 1.5 CB. Then in span BD, the fixed end moment at B as well as at D is 0. So we got it 0 here and 0 on the other end. Then below the fixed end moments, we are going to release a C. The reason as why we are releasing C, it's because it is simply supported. And remember, in our previous video we said that whenever we have a fixed end, that is, whenever we have a simply supported end or a simply supported joint, we are going to release it to balance it. And in this case, the fixed end moment at C, at joint C for member CB is positive 1.50. So we are going to release it with an equal and opposite moment. So we are going to have negative 1.50 so that the resultant moment gives us a 0. So the support C or the joint C will have balanced in that form. Now, after we have released, it will be followed automatically by carrying over. So we are going to carry over half of this moment from joint C to joint B. And remember, the carry over factor is a half. So a half of negative 1.50 from C to B, that is negative 0.75. And then next, we can now have the initial moments. So to get the initial moments, here we have negative 7.20, we write it there. Positive 4.80, we write it down here. We got 0 on member BD. On member BC, we are going to add negative 1.50 plus negative 0.75, which is negative 2.25. Then on member CB, 1.50 minus 1.50, that is 0. And then on member BD, we got a 0. After writing the initial moments, it will automatically be followed by distributing. Now, when we are distributing, this is what we are going to have. We are going to take negative, we are going to take 4.80 plus 0.00 plus this one. Now, remember, when we are distributing, for us to get the excess moment, we usually change the signs of our moment. So, in this case, we are going to have negative 4.80 plus 0 plus 2.25 plus 2.25, and that's going to give us what? We are going to take this 4.80, we change its side, it is going to be negative 4.80. Then we add this 0, definitely there's nothing. Then this 2.25, which is negative, is now going to be plus 2.25. And that is going to give us negative 2.55. So that is the excess moment at joint B, and that's what we are going to distribute on each member using the distribution factors. Now, on member BA, we are going to have negative 2.55 multiplied by 0.407, the distribution factor for member BA, and that's going to give us negative 1.04. For member BD, we are going to have negative 2.55 multiplied by the distribution factor for member BD, which is 0.340, and that's going to give us negative 0.87. For member BC, we are going to have negative 2.55 multiplied by the distribution factor for member BC, which is 0.254, and that's going to give us negative 0.65. Then after distributing, we are going to carry over, and in this case we are going to carry half of this moment of negative 1.04 from joint B to joint A. So half of 1.04 is negative 0.52. On this other end, we are going to do the same. On joint B, we are going to carry half of this negative 0.65 from joint B to joint D. We cannot carry it to joint C because C, we have already balanced it. So if at all you carry it to C, you are now going to have an unbalanced joint at C, which we don't want to do. So we are going to carry half of 0.65 all the way to joint D, and that's going to give us negative 0.43. So for this one we don't have anything to carry over. For this one we don't have anything to carry over, so we got zeros, and that's going to be the last part we are going to have. And then finally we are now going to have the final moments, which we are now going to use to plot our bending moment diagram. And for the final moments, we are going to take the initial moment and then add the moments that are below the initial moments. So for member AB, we are going to have negative 7.20 minus 0.52, that is negative 7.72. For member BA, 4.80 minus 1.04, that is 3.76. Here we are going to take this one direct because these are zeros. Then for member BC, negative 2.25 minus 0.65, that is negative 2.90. Then here we have 1.50 minus 1.50, that is a 0. And then here we got negative 0.43. Then after getting the support moments, the last thing we are going to determine are the bending moments as a result of the vertical loads. So let me look for a space here where I'm going to determine the bending moments due to vertical loads. Awesome. So we go to, where the heck is my black pen? So we go to bending moments. So bending moments, and in this case we are going to begin with bending moment for span AB, and the bending moment for the span AB, the span AB is loaded with a point load of 10 kilonewtons. So the bending moment at where? At E will be given by this formula, WAB divided by L. This is going to be 10, which is the point load, multiplied by A, that is A to E, 2 meters, multiplied by B, which is 3 meters, divided by the whole span, which is 5 meters. And that's going to give us a bending moment of 12 kilonewtons meter. Then we go to the span BC and we determine the maximum bending moment. It will be given by WL squared divided by 8, since that span is loaded with a UDL. So this will be given by UDL of 2 kilonewtons per meter multiplied by the span 3 meters, we square that, divided by 8. And when we do so, that's going to give us a bending moment of 2.25 kilonewtons meter. So we are now good to go and plot our bending moment diagram. Now let's begin with the bending moments as a result of vertical loads. Starting with the span AB, the moment at E is 12 kilonewtons meter. So let me get it at that point. So you're going to join that to A. Yep. Then we join the same to B. Make this one straight. Yeah. Then we join the same to B. Exact. Yep, so here we have a bending moment at E of 12 kilonewtons meter. Then we go to the span BC with 2.25. But before I draw it, let me plot the support moments. At A we have negative 7.72, just below 12. So here we have 7.72 kilonewtons meter. We join that to the horizontal line. Then at B, we got 3.7, that is for member BA. We have 3.76, so 3.76, and we have it here. So we join 7.72 to 3.76 kilonewton meter. So 3.76 kNm. Then on member BC we have negative 2.90. So 2.90 is about that point. So drop that there. Yep. Then bending moment at C on member CB, that is going to be 0. So we join 2.90 to 0 at C. So that is how it is going to be. Oh, very good. So here we have a moment of 2.90 kilonewtons meter. Then the maximum bending moment here is 2.25. So 2.25, about that point. So that's going to be a smooth curve. This is the bending moment due to the UDL, or due to vertical load. Very good. So here we have a maximum bending moment of 2.25 kilonewton meter. Then from there we have the bending moment on the span BD, which is 0.87. So 0.87, say approximately that point. Then on DB, remember DB, joint D, at joint D we have 0.43. So 0.43, let's say about that point. So we are going to join this 0.87 to 0.43. It will look like scissors, eh? Musaraba. Awesome. So we got a bending moment here of 0.87 kilonewtons meter. And then at this point we got 0.43 kilonewtons meter. So that's now our complete bending moment diagram, and to completely complete it, we are going to shade off its outline for it to be clear and visible. Awesome. So ladies and gentlemen, that's how we plot a bending moment diagram for such a flame. So this is going to be negative bending moment. This one is positive. This one here is a negative bending moment. This one is positive. This one is positive, whereas this one is negative. So that is now our complete bending moment diagram. So thank you very much again, ladies and gentlemen, for watching our video. If you aren't yet a subscriber, hit that subscription button. Also don't forget to hit the notification bell. We upload a new video, you get notified. Very good. So let's meet in yet another episode, another lesson. Thank you.